let's talk about Maxwell-Boltzmann distribution curves, which essentially show the distribution of molecular energies. So we can think of it like if we took all of our reactant molecules, right, taking part in a chemical reaction or in like a reaction vessel, and we considered how much energy, how much kinetic energy each of those individual molecules had, this would be the distribution or the spread of the energies. So if we now construct the curve with that in mind, because we would not be carrying out this reaction at 0 Kelvin, all of the molecules will have at least some energy. So with our axis here of our number of molecules on our y-axis and our kinetic energy on our x-axis, we know that there are no molecules, right, 0 molecules that have 0 kinetic energy. So we must start at the origin 0, 0. Then as the energy starts to increase, there are going to be, more and more molecules with that energy. And then most of the molecules will have kind of, middle-ish energy, right? Average-ish energy. And then as we start to get to much higher energies, there are going to be fewer and fewer molecules with super high energies. Now, our curve is not, and I repeat, not going to touch the x-axis. And that's because even at super high energies, there's always a chance, right? There's always a chance that there's, one rogue molecule that's just got a crazy amount of energy. So we can't say for certain that there are no molecules with these really high energies, which makes our curve an asymptote, right? Asymptotic, am I saying that right? I don't know, call a maths teacher. So it's not going to touch the x-axis because there's always a chance that there's going to be a molecule with that really high energy. So we're going to get close to the x-axis, but never quite touching it, just closer and closer and closer. So that is our general shape. Just labeling this again to kind of consolidate what we've just spoken about. There are going to be no molecules down here with no energy. We are going to have most of our molecules with kind of middle-ish energy. And then we are going to have fewer and fewer molecules with high energy. Now, that helps us to explain why chemical reactions might be slow and how we might increase the rate of a chemical reaction. Because if we consider the most likely energy that a molecule will have is down here. So I'm going to label this actually quite handily. I'm going to label this the most probable energy. Right? It's the energy that has got the most molecules. There are no other energies that have got more molecules with that energy than this energy here, most probable energy. Then slightly to the right of the most probable energy is where we're going to get the mean energy. Now, the reason that the mean energy is slightly to the right of the most probable energy is because these few molecules with really high energy are going to kind of distort the mean a little bit, so shifting it to a little bit higher energy than the most probable. So most probable at the peak and the mean energy slightly to the right of the peak. But the most important energy that I need to label on this curve is, of course, and you're probably already saying it to me, shouting it at me, is the activation energy, which we'll write kind of somewhere over here. Right? There's not a set place for the activation energy, but it's just usually towards the right-hand side and like the tail end of the curve. And the activation energy, which I've denoted as EA, is the minimum energy required for your reaction to take place. In the simplest terms. Because we know from collision theory that for a collision to be successful, it needs to be in the correct orientation and needs to collide with sufficient energy. I always clap to show it, okay? Has to collide with sufficient energy. And sufficient energy means the activation energy. That is sufficient energy. So with the area under the curve, the total area under the curve being the total number of molecules, this area just to the right of the activation energy represents the number of molecules with sufficient energy for a reaction to take place, right? For your collision to be successful. So we say that these are molecules with energy greater than or equal to the activation energy. Only these collisions will be successful. And I'll say it again, only these collisions could be successful. So this can now help us to explain how adding a catalyst or changing the temperature can affect the rate of a chemical reaction, and how we can show this on a Maxwell-Boltzmann distribution curve. If we start with a catalyst, because that's going to be the easier one to show, we know that a catalyst, where should I write this? I'll do it up here. A catalyst lowers the activation energy, right? It does that by providing an alternative pathway for the reaction to take place. So if we're lowering the activation energy, I'm going to now label on my curve a new activation energy that is lower in energy than the original one. So instead of over here, my original activation energy, how many times can I say activation energy? I'm going to put a new activation energy at a slightly lower temperature, not lower temperature, lower energy. Oh my goodness, you're in the way. Sorry, kinetic energy. Is the word energy starting to sound weird to anyone else? Just me? Okay. Right. Lowers the activation energy. So I'm going to draw my new activation energy is now going to be here, and I'm going to call that ECAT, the catalyzed activation energy. So that means that as well as these molecules that had energy greater than or equal to the activation energy, so sufficient energy for a successful collision, now these additional molecules also have sufficient energy for the collision to be successful. So how does your catalyst increase the rate of reaction? Well, by lowering the activation energy, there are now more molecules. I don't like this pen, but I've started, so I'll finish. More molecules with energy greater than or equal to the activation energy. Therefore, more frequent, successful collisions. Nice and straightforward. Now, when it comes to temperature, now it's not so straightforward as just changing a label on your curve. Because if we change the temperature, we're now changing the amount of energy that your molecules have, right? Because increasing the temperature is giving the molecules more energy. So how would that affect your distribution of molecular energies? Well, if your molecules now have more energy, then your molecular energies are going to be shifted to higher energy. So we're going to shift over to the right, and then still the general shape, same shape as before, but notice that the peak is slightly over to the right. We've increased the most probable energy, and the peak is slightly lower. And that's because, as mentioned before, the area under the curve represents the total number of molecules. So because we've now got kind of more over here towards the end, we need to make sure that the total area under the curve at the higher temperature is still about the same as the total area under the curve at the lower temperature, which is why your peak ends up slightly lower as it shifted to the right. Now, how does that affect the number of molecules with sufficient energy for a successful collision? Well, we would look back at our original activation energy, okay, because changing the temperature does not change the activation energy. But now, as well as these green molecules that had enough energy to react, now also at our higher temperature, these additional molecules also have sufficient energy to react as well. I'm going to label this as a higher temperature. Okay, so with an increased temperature, we are still going to have essentially the same effect by giving the molecules more energy. Have more energy, kinetic energy. Therefore, there are more molecules with energy greater than or equal to the activation energy. And those are essentially the key things that you need to know for your Maxwell-Boltzmann distribution curves. For more practice and just more A-level chemistry support in general, make sure that you are subscribed. Make sure that you comment if you've got any questions, like this video, and I will see you in the next one.